So I welcome all the participants and the speaker to the last session of our faculty development program. So we have Professor Chittaranjan Hota sir, who is senior professor in Department of Computer Science and Information System, BITS Pilani Hyderabad campus, Hyderabad. So sir will discuss about building smart IoT system, some of the challenges and their solution. So before sir will start the session, I will introduce sir to all the participants. So Professor Hota is a senior professor in computer science engineering at BITS Pilani, Hyderabad campus. He completed his PhD in computer network from BITS Pilani and has more than 33 years of teaching and research and administrative experience in India as well as some of the universities in abroad. He has received fundings from various funding agencies, both from India and abroad. His research work on information and system security, big data analytics, cognitive IoT, and some of his works are funded by MIT and DITY, UGC, DST, Intel, TCS, Progress, NWO over past several years. His current research on devising secure algorithm for BioCPS devices has been funded by DST under NMI's ICPS scheme. He guided more than dozens of PhD scholars in his areas and published more than 150 research publications in various reputed conferences and journals. He is visiting researcher and professor at several universities abroad over the past few decades, and universities where he has spent a significant amount of time pursuing teaching and research includes our Alto University, University of Cagliari, Italy, City University London, UNSW Sydney. He has been involved in various administrative positions of BITS Pilani over last 2 decades. Some of the notable positions are Associate Dean Admission, Professor in Charge University Exam, Faculty in Charge Information Processing Center, and Head of the Department of Computer Science Department. He is active member of IEEE and elevated to senior member long back. So with this small bio, I request Professor Chittaranjan Hota sir to start the session. Sir, please.
Thank you, Dr. Sanjay. So let me just share my PPT. So can you all see my screen?
Yes, sir.
Okay. So is this visible, the first slide?
Yes, sir.
Yes.
Okay, thank you. So let me formally thank Dr. Sanjay and Professor Asmiranjan Raut, who have given me this opportunity to speak to all of you. And thanks, Dr. Sanjay, for introducing me to these participants of this online FDP. If you see my title, this is Building Smart IoT Systems, some issues or challenges and their solutions. So what I'll do is, through this topic, I'll try to give you a summary of 2 of the research works that we have done over last 4 to 5 years. So one got over last year, and one is continuing, which possibly will go for 1 or 2 years more. So with this, let me now start. And I would love to get interrupted whenever somebody feels okay or has any question. You can simply raise your hand and then ask a question. And I hope it is 2-hour session. And Dr. Sanjay, if I'm right?
Yes, sir. Yes, sir.
Okay. All right. So let me start now. Fine. Before I go and take you through my content, let me acknowledge the people who have funded these projects. So as Dr. Sanjay rightly mentioned, these 2 projects that I am presenting here on this session are funded by these bodies, Ministry of IT, then NWO, which is the Government of Netherlands, then Cisco, Intel, Progress Software Hyderabad, then TCS, Tata Consultancy Services India, and then DST for the ICPS project, the current one which I am doing. This is the outline of my talk. I will introduce the topic, and then I'll also, through that introduction, I'll also take you through the journey from AI to deep learning, or maybe generative AI. Nowadays, what we call the last jargon, right? The latest jargon that we call. After deep learning, we are all using this word, generative AI. So I'll take you through that landscape. Then the IoT evolution, right? How IoT was evolved, from which state, through all those intermediate states, it came up to the IoT evolution, and also what is the meaning of cognition or cognitive IoT or intelligent IoT. So I'll also talk about that. Then what are the possible architectures? As the title of this FDP is about cloud, fog, and IoT, so these three go hand in hand, right? So I'll talk about those three aspects while covering this IoT architecture, and also what are the top concerns while building an IoT prototype or IoT test bed or an IoT real world application. Then there are some solutions or techniques that we have used through these two projects that also I'll discuss, and finally I'll conclude. So here, if you see, I've given the title as Homo sapiens, right? Man the wise. We all are Homo sapiens because we evolved from the biological species called as Homo till we are now Homo sapiens, right? The human being, be it a male or a female, right? We have a intelligent brain, or we are all intelligent. Maybe the degree of intelligence varies from person to person. Doesn't matter, but everybody has some degree of intelligence. So let us decode that word intelligence. What do you mean by intelligent behavior? Now this is all there in the power of mind, right? Our brain has around 10 to the power 12, a very large number of neurons. Now these neurons are nothing but brain cells. They help us in storing, processing, right? Doing a lot of intelligent activities inside our brain, and hence. If you see the quote from Swami Vivekananda, the great philosopher from India, so what he said, we are what our thoughts have made us. So take care about what you think. Words are secondary, thoughts leave, they travel so far. So the way you think in your mind or in your soul, right? These thoughts will result in a set of habits that we do on a day-to-day basis. Those habits will define our behavior, and behavior will define our character, and this character will also define or will give us what are results in our life. So ultimately the goal of an intelligent being, human being, should be, in nicer terms, should be to live a happier life, right? Irrespective of what are the problems, what are the issues that come up to him on a day-to-day basis, he should lead or he should live a happier life, right? Maybe for a longer period of time, out of, let's say, 70 to 80 years, the life expectancy period, someone who is happier for, let's say, 60 to 65 or 70 years, and maybe 3-4 years in the middle or in the beginning or towards the end, he was not happy, it's okay, it's fine, right? So this type of activity or power our brain gives us. As I said, 10 to the power 12 neurons you will find in a healthier man's mind, and this mind actually carries out a lot of intelligent activities. You can see here, what are those mental faculties or powers, right? The activities that we do. We all have imagination power, we all have perception, we all have willpower, right? People who are having strong willpower, they do difficult tasks finally successfully, right? We all have memory power. Like, for example, there are such a set of people who will recognize their class second or class third teacher, although they are meeting them after 50-60 years. right? This is all coming from memory. We have intuition power, right? We can intuit something to be happening in future, right? We can also reason out. Logically, we can find out why this has happened. What are the causes of this outcome? So all these 6 mental faculties make us intelligent human being. But again, it varies from person to person, as I said. Not necessarily everybody will have 10 to the power 12 neurons. Somebody will be having lesser number of these neurons, and they may not be getting that much excitation or that much power or energy to carry out all these 6 activities in a very fulfillment or very nice manner, right? But yes, we all are intelligent. So hence we are called as Homo sapiens. So human being is intelligent, it's all okay. But unless we are connected to different people, right? For example, I met Professor Rasmi on a conference, right? And then maybe I got connected to Dr. Sanjay through him, right? And then maybe I got connected to all of you through this particular program. So this is all maybe how are you making connections to different people in the world? The more you will be connected, the more activities or intelligent activities you will be able to do, right? So if you see this, there was a research by an anonymous hacker way back in 2012. What he was trying to do was to find out, do an internet census, right? Finding out how many people are actually using the IPv4 addresses in internet. There are roughly around 4 billion IPv4 addresses, because it's a 32-bit IPv4 address, right? Now, out of those 4 billion people, what this researcher did, he could figure out the usage of around 1.3 to 1.4 billion IPv4 addresses throughout the whole globe. You can see the color code. This is basically between day and night of different parts of the world, where he used around 400,000 bots or programs installed on different computers to create a botnet and use the default credentials, like login is user, password is 123. So there will be computers with these default credentials, or there will be routers or switches with these default credentials. So use this to figure out if those computers are using internet or not. That he was able to do. So you can see here, it's a very good response that he got. But fortunately, the same gentleman published his research and then maybe apologized to the community, saying that without taking the consent, he was able to reach out to different computers to just figure out how many people are using this internet at a point in time. So basically, what I was trying to say in this slide is, we are all connected, right? Everybody has at least 30 or 40 people all over the globe you must be knowing, right? Some of us. So there is a 6 degree of separation, if you see, that is there in theory, where if you take any 2 person in the world, you will find them connected through 6 different hops, 6 different intermediaries, right? So this is also giving us activities or power to carry out a lot of or implement a lot of actions or applications. It is not only connection and intelligence, we need to also have data, right? Maybe I have a lot of connections, but I don't talk to anybody, right? I don't share anything with anyone. I don't see anybody's posts, right? So then I'm not contributing to this growth of data. So here, if you see, this is coming from Statica, where let's say in 2024, you'll find 147, around let's say 147 or 150. This is data volume in zettabytes. So zettabytes is nothing but 10 to the power 21. So 147 zettabytes is a huge amount, and then possibly by 2025 it might go up to 180 or 181 zettabytes. This much data we have currently on internet. Few examples. If you see Google, 8.5 billion searches per day that happens in Google, right? Which is a very big number. We are all in India 1.4 or 1.5 billion people. You can see the number of searches are 6 times or maybe 7 times than what our population is. Look into Facebook or Meta. out of 3 billion users that, or 3.5 billion users, total users that Meta has currently, 2 billion users are active per day, which is a very huge number. And today, if you see how many people, entire world has around 8 billion people. Out of these 8 billion, 5.5 to 6 billion people are using internet. From that, again, 7 to 60, 65 to 70% people are using these social networking sites. So hence, there is a huge amount of data that gets generated or pumped from different users, and it gets processed by different applications. Now, let me go to the next area where we have all this data. What will you do, right? Unless we have a nicer technology or a technique, engineering principle, we can't generate a lot of intelligent insights from that data. So hence your AI ML area comes into picture, right? And over last, let's say, 4 to 5 years, we all have witnessed different academic institutions, right? Almost every academic institution has gone up and then started new programs on AI, ML, deep learning, generative AI, right? IoT, data analytics, big data analytics. So roughly around 8 to 9 different courses and 3 to 4 different areas have evolved. Minor in data science, minor in computing and intelligence, all that have happened. That is all because of this AI ML growth. Here, if you see in this slide, the top 2 gainers of this AI area are China and North America. So China has around 26.1% of the GDP total impact of this AI ML area, and North America is around 14.5%. So India is picking up over last 3-4 years. We have invested a lot on this. Now, if you see these 2 bullets, where the CAGR, compound annual growth rate, CAGR of this AI global market, is around 37.3%. That is the prediction from 23 to 30, 2023 to 2030. Whereas for India, the CAGR is not lagging behind, right? It is around 33.28%, which is just 4% less than what the global CAGR is. And our market is also stronger, right? Healthier. You can see $680 million in 2022, and possibly by 28 it will reach 3,935.5 million. So today, if you see this AI ML area, it's around 200 billion, let's say, globally, right? And possibly it will reach to, as it is predicted there, 1.8 trillion or $1,811 billion by 30. So if you compare the amount of money that this AI ML area is giving, it is none less than the defense sector is giving. So defense sector possibly is around 2.2 to 2.4 billion globally. Where so almost every country spends more on their defense budget. So this AI ML is just 4 to 5 years old area. So this is now reaching towards that budget globally. Hence, there is a huge potential that is available on this particular market, where people are all now starting to think of using this AI ML to develop innovative applications, right? Innovative products which can be useful to different human being or different population. Okay, now let me go through the journey from AI to, let's say, deep learning or generative AI. Let's say in 1956, this word was coined, this AI, artificial intelligence, by John McCarthy in a Dartmouth University conference, and hence he is named as father of AI, right? From those days, now AI has come a long way. So it is around 40 plus 25, let's say 65, 70 years old. But you can see during the initial ages or initial days, those are all good old days. Let's say Elijah, it's a Rogerian psychotherapist, where it can help you in understanding state of the mind by doing a little bit of NLP. Right? You can see a left-hand side conversation with Elijah. So it does all that. It throws you responses based on certain keywords that are already available in your communication or conversation with Elijah, and responses were stored inside it, right? There was no ML or there was no intelligence involved in this, but it was first NLP program coming from MIT's AI lab. But whereas we have now very intelligent NLP programs, let's say ChatGPT, right, which is the latest version of maybe a program like Elijah you can call. Another image you can see in the right hand side, Shaki robot. It's a electronic, so it is the world's first electronic person, right? Person means it has the power to see, right? It has the power to move. So it was a robot which was designed by this SRI, Stanford Research Institute. But we have now nicer robots all over the world. I'll talk some of those as I move. So these are all some of the initial AI products. Yeah, this was also a good product to be recognized during, let's say, 1997. So IBM came up with a machine and a software called as Deep Blue, which defeated Garry Kasparov. You can see Kasparov, the Russian grandmaster, right? The chess champion, world chess champion, who is playing with the IBM Deep Blue, where 96 Kasparov defeated Deep Blue, but in 97 Deep Blue defeated Kasparov, right? So it's a chess program. Now, if you see intelligent or AI program must have done this or has done that, right? Now, how many number of states are there in a chess game? If you see, now one state you can see here on the board, it is looking like. The moment one of the player makes a move of one of its element, you will get another state. So basically, you are searching through this state space, moving from one state to another state. Maybe initial state is where everybody is in the initial position, and the final state is where one's king is under attack by the other player, and the king cannot move. So game ends there. That is the final state. So you have to start from the initial state, go to the goal state, traversing through this state space. So there are around 10 to the power 120, right? 10 to the power 120, a very big number. This many number of states you will find in this chess game. And Deep Blue, the program, it actually did a iterative deepening search. It's a type of heuristic search. It did, and it used a cutoff technique called as alpha beta pruning, where it avoided certain paths based on certain intelligence or certain heuristics, right? Or those two metrics, alpha and beta, at two different levels, maximizing and minimizing level, min-max player game. And then finally, in 1997, it defeated this Kasparov. So this was also one of the good old day product. Then we can see so moving from AI to real intelligence. We are all living now. We call it as now no more artificial. It is really we are getting intelligence from computers, right? There are a lot of movies also got produced on this AI, right? One of those was the robot, the Chitti, Rajnikant's movie, where you could have seen the Chittis behaving differently from time to time, right? So there was a phase where it was also, or it is behaving like a destroyer of its creator. So those all things are coming from this not artificial, it is coming as a real intelligence. Now you can see AI is at a broader space. Then machine learning is a subdivision of AI or is a part of AI, and then finally deep learning is a part of machine learning. And we are nowadays uttering another word called as, let's say, generative AI, which is nothing but a part of deep learning. Okay. So now let me give you 2-3 examples of these to distinguish these three. Let's say Hyderabad to Dwarka, right, which is Lord Krishna's birth, that is city, right, in Gujarat. If I have to travel from Hyderabad to Dwarka and I want to prepare a travel plan, right, which technique I should use? Should I use a AI technique or a machine learning technique or a deep learning technique? So AI technique is enough, right? Possibly it is a planner which I can devise, which is a type of heuristic search technique through which I can prepare this plan, travel plan. Now it is difficult to program this computer to make it understand what I want to do it, right? Let it do it by itself using right structure and a set of examples. I'll give a set of examples, let's say be it supervised or unsupervised, and let the computer figure out how to do it, right? That is, or how to do it, or what should be the output for a new input that you are giving. For example, in the image you can see the way we detect spam emails, right? So let's say by telling machine that a mail where you have words like boss, BOSS, words like hiding, words like money, words like let us meet, right? Some of these, so you can basically tell the computer and then decide. Of course, you have to define an algorithm, or you have to give it an algorithm, and then it will learn by itself. So that whenever you give a new email, it will classify that one as a spam email, which Gmail also does by using a SVM sort of algorithm. Then come to, let's say, deep learning, where you can see, I do not know how to make this computer understand what I know. Let it create its own structure and figure out the data for itself. So neither the algorithm nor the data that I can educate my machine learning algorithm. Basically, these are all neural networks, right? Whereas in machine learning, you can have both symbolic as well as neural network based, ANN based. Whereas in deep learning, these are all neural networks where you leave it to the computer to come out with its own structure, right? How many number of layers should be there, how many number of nodes it should take, what should be the weights on all those links. So that is how the deep learning models work. And you can see the image classification, let's say, is one example of a deep learning model. Now let me take you through few applications. So the first one that you are seeing is here a self-driving car, right? Now the market size of this self-driving car is will be around $62.4 million US by 2030, with a compound annual growth rate of around 13.3% between 21 to 30, right? Which is a huge market. And maybe in India we have not seen these self-driving cars in reality, whereas in US you can see Waymo, which is an Alphabet Inc.'s company, that is Google's company, where the Waymo taxis are running in these cities: Arizona, Phoenix, San Francisco, Texas, Los Angeles, right? Cruise, another taxi from this. It's running on San Francisco. Uber is also running on these smart cars on this Miami, Phoenix, Pittsburgh. So they are all cities on which smart cars are currently operational. But of course, you can see how it is a part of a deep learning. When a car actually starts, it is equipped with a lot of sensors, right? It can see its entire environment. Whether a car or a four-wheeler is coming from the opponent side, right? Or traffic lights are there on the opponent side, how much distance it is making to the one corner of the road, all that it can judge. And then the learning model will help it, learning, reasoning, all those will be there, right? Mostly these are all deep learning examples where it will figure out a nicer route by itself, getting into getting the passenger from one place to another place. Even these days, there are a lot of simulations which are also going on through these generative AI models on these smart cards, where they can experiment with different type of accident scenarios or road accidents which are not which have never been seen, because they can generate those new instances, and hence they will be much more powerful in doing their normal activities from time to time. So this is one such application. Yeah, one more application under your deep learning model is these LLMs, large language models, right? The animation that I'm showing is from Google's Lambda. This is a product from Google. Of course, OpenAI has its own product, ChatGPT, which almost everybody is, or maybe many people who are into internet, right? They're all using that ChatGPT to get their answers or responses. Sometimes we also use as academicians to figure out what could be a best way to pursue certain areas of research. Now, in this animation, you can see how so basically a person is interacting with this Lambda, where he is saying that I would like to have a conversation, right? Now, you can see the response. The person is saying that if my washing machine and TV both are malfunctioning at a time, then what could be the reason? So Lambda is responding, saying the reason could be there could be a power surge, right? There will be a power fluctuation in your home because of which these two devices are malfunctioning or not working. Then the person is giving a pause, and maybe it is, yeah, maybe, by the way, how many legs does a horse have? So immediately changing his context, right? The person. So he's agreeing, okay, there could be a possible power surge. I agree to your response. But it is again asking immediately how many legs a horse will have, right? You can see that in the next. Now, and could it fix my washing machine, right? So he's asking that is your horse is able to fix that problem. Then the Google Lambda is responding, no, horse has 4 legs, and maybe it is silent on whether horse can fix the washing machine or not, right? It is saying horse have 4 legs, how could they help, right? The person is saying, you tell me. And then the LLM model is not stopping there. It is saying, okay, if you move to, okay, horse can take you to your home where you can repair your TV or washing machine that you have. So this LLM model, what you just saw here, is basically generating new content, right? Now, you can also have, this is all textual based. You can also have image based or videos, right? Any type of content which can be generated, a phrase which has a context, which has a meaning to the previous content or previous information that you had seen, right? So these are all again using generative AI models. So they are all basically transformers, right? Bot models, and through which they do all these newer content generation actions. The last application that I'll take here is deepfake, right? Some of you must have heard this news. The recent one is this, probably Aviator is a game app, right? A betting app where somebody can bet money on that app, and Sachin Tendulkar's some previous conversation or the voice, etc. They are trying to now superimpose or mix with this particular app, which he has not told actually, right? So it's a fake content which has been generated by using again these generative AI models. As I said, newer content you can develop or you can prepare or you can generate by using these generative AI models, where maybe it is, if you see that video where Sachin is, he's actually not saying, but the video says that, yeah, my daughter is playing this app, so you all can play this, and it is a good app to give you good money quickly. And maybe this was 10-15 days ago. And the 4-5 days ago, the same type of video has come even for Virat Kohli, right? You can see another deepfake news, maybe it was in January 20, where Delhi police have arrested a main accused behind the deepfake video of Bollywood actor Rasmika Mandana, right, which went viral on social media post last year. It was in 2023. The mastermind behind the deepfake video, identified as E. Naveen, was an engineer and allegedly wanted to boost followers on his Instagram handle. Right now, in the deepfake video, Rasmika's face was superimposed on a video of a British Indian influencer, Jara Patel. Jara Patel was actually dancing, but they superimposed Rasmika Mandana's face on that image. Right. So there are again so many such wrong incidents or bad incidents which have taken place on this deepfake. Using this deepfake technique, right? Which is again not a good sign for the technology. But again, Indian government is proactive. I think I was hearing over last 2-3 months, Ministry of IT and other entities, they have now tightened the noose. They have gone for making newer rules on the social networking websites or platforms to stop immediately these contents or possibly arrest or take legal action on the people who are getting involved in such activities. Right, let me just pause for a while, and if anybody has any question on this, I would love to take, and then I'll go to the IoT part. Yeah, if there are any questions for me till now.
You are explained clearly, sir. No doubt.
Okay, thank you. Thank you. So let us now go to the next part, where I think this is all about what I said, why AI or ML is being, I think, recognized as a strong technology to give you that around $1.8 trillion in another 3 to 4 years, which will compete with the defense budget globally or worldwide. Fine. Now, okay, so every technology has its positive side as well as negative side. But if you actually ask people who think positive or talk positive, they all will say that this AI ML is not going to create any harm to maybe the number of jobs, right, or the number of type of jobs that are there in the IT world. However, there are a set of people who will also give you some sort of fear, right? A lot of job cuts are happening because of AI, ML and all. It is not true, right? So, in my own view, it is not true, and it will basically augment. It will basically help you in strengthening what we are doing. But of course, we need to educate, or we need to change our gear so that we are learning these techniques, how to develop an app, or how to develop one such, or how to use one such intelligent app regularly. Okay. So now let me come to this IoT. I will talk about evolution, how these IoTs have evolved. Right. We all know that it is so thing could be, let's say this pen could be a thing, right? Maybe my smartphone could be a thing. My watch could also be a thing. These are all non-living beings, and I also could be a thing as a human being, right? Maybe the process, for example, we have a ERP process through which we apply for our leaves. That could also be a thing, right? So, all these things, right? What you do is you connect them and get a gather data from all these things, put them all into some sort of connection on using internet, and then develop applications using those hardware as well as software. Now I'll take you through this landscape in my next 2 or 3 slides. So you can see human to human communication. This was pre-internet era, before ARPANET, let's say before those 1950s, right? So ARPANET was the first network that was created by 3 to 4 United States universities. Now those 4 or 5 universities, they were wanting to have some communication amongst themselves through which they could share certain information, right? They could get some information from one organization to another organization. So that was the purpose, and slowly that got evolved or enlarged to what we are seeing today. Internet is, right? Of course, There are a lot of ISPs, there are a lot of other entities, government organizations, right? Private organizations. They all are involved in making this internet a reality. And of course, Internet of Things is an extension there. It is not only human being. We should also talk about other things, right? Other objects. So pre-internet era where people were using telephone handsets, you can see. Then came your computers were developed and computer networks also came into existence. Then Internet of Content, right? So for example, that was called as Web 1.0. This was again during those 1960s, 60 to 70 or 75 or so. So Internet of Content where applications like World Wide Web, www, right? You have a browser and you are sending a HTTP request, getting a HTTP response. The web page is coming to you and you are seeing the content of that web page. So organization is making available that web server for letting all the people know about what they do, what are their functions, what are their services, right? How do they operate? So all that they are trying to make available through that website, and people are coming to know through this application, right? World Wide Web. Similarly, we also saw a few other applications like SMTP, mail gateways, where you can send a mail from your site to another site using again. So there will be two SMTP gateways which will be used in the backbone, and those two SMTP gateways will talk to each other and will help your mail getting delivered to the other party over the globe, right? Even we saw applications like FTP, file transfer protocol, right, where you can transfer a file from one place to another place. This was all about Web 1.0. Then came Web 2.0. This is a new next evolution or next development that happened. So each of these developments were they were taking around 10 to 12 years or 10 to 15 years period. So there are a lot of platforms which got developed and a lot of services came into play. That is Web 2.0. So that is, for example, Internet of Services. For example, today we have this Swiggy, right? Zomato. We have Amazon. We have Big Basket. We have Flipkart, right? So e-commerce site, food delivery sites. Even we have those postal deliveries, right? They also are now. So see, why you need a platform? Because if it is a Big Basket application, somebody has to bring those grocery items from the Big Basket's main store, where they might have accumulated from different sellers, to the end host, the user, right? So there should be a bike, or there should be a truck, or there should be a auto through which this person is coming. So this is one of the requirements, right? Similarly, you have all these Swiggy boys or Zomato boys, right? They all travel by bikes and then take your food item from one place to another place. So this is all your Internet of Services, right? Then the smartphones became cheaper, right? From last, let's say, 15-20 years, 10 to 15 years you can take. Now, I remember, let's say, the Nokia smartphone, which was coming during those days, the 90s or 95, 97 and all that during time, that was costing us around 7,000 to 8,000, right? A good Nokia handset, which was running again a Symbian Unix on its device, right? Which was a proprietary one. People, if there is a problem with that Nokia handset, you have to go and then wait for 3 to 4 days to get it, right? Because it was not open source kernel or open source OS like what we have today, Android phones. So smartphones, there are softwares which were there on those smartphones, and then there are a lot of applications also developed. But yes, people got involved into this Internet of People. Next application, Web 3.0. So when I say Internet of People, let's say Facebook, Twitter, right, Orkut, so LinkedIn. So for example, LinkedIn we use for possibly as a professional activities which you do, right? We come to know which of my friend who is connected to me through LinkedIn knows, let's say, a particular type of language, maybe a C#, right? Or a language like Go, so that I can reach out to him to get some help, right? Or who is my friend who is, let's say, a CEO or a CTO to whom I can send my resume to get a job. So that is how we all have LinkedIn. And of course, Facebook is on Meta is now the application which around, let's say, out of 1.4 crores people in India, right? Around 70 to 80 lakhs people are using these Facebook, right? 70 to 80% is it's the usage within India. And of course, as I said in the beginning, from 8 lakh of people in the entire world, with around 5 to 6 lakhs in using internet. From there, 3.5 to 4 billion are using Facebook. So it's a huge amount of data that comes into the platform. And from each user who is having an account in Facebook, Facebook earns around 18 to 22 or $25, which is a huge amount for Facebook by using those advertisements, right? So it depends on entirely the ad model to give you all that to provide the services. But yes, Facebook never stops you from keeping all the content to within yourself, right? It does not tell that you, unless you give some contents you cannot access. No. Whereas there are a lot of other peer-to-peer sites, for example, torrents, where if you are a selfish user who is only seeing others' content but not giving his own content, there will be some penalty, right? Whereas we don't have any such regulation or issues in, let's say, social networking sites like Facebook or Hota or maybe the LinkedIn, Twitter, etc. Next came this machine to machine, right? Internet of Things, IoTs. This is all because of devices and objects. Now, the IoT is not just about locating objects and using them to sense the surrounding environment or accomplish automated tasks. It could be a wearable to a jet engine to a connected fridge. We can have all these devices. And smart light bulbs also could be part of this IoT. Sensors today are costing us, let's say, a few hundreds, right? Maybe 300 to 400. And if you see these Fitbit watches that we have are again costing us from 3,000 to, let's say, 20,000 or 25,000, right? Now, the business world is now starting to recognize that by combining the sensor data with a variety of other data sources from inside or from the outside of the organization, it can save a lot of costs, right? Deliver operational efficiencies and support new types of business models. So hence, a lot of organizations or corporates are now thinking innovative ways by which they can do their business using these IoT paradigm. For example, a German company named as, let's say, Caterpillar, right, which produces construction and mining equipment, the manufacturer of those equipments, are producing applications that can give their drivers an insight into the fuel level, right? The fuel level in the tank and the condition of the air filters in their vehicles, or maybe condition of pressure on the tires, etc. Automatically they can get those. Now, these IoT are not only sensors, they could also include devices like fog nodes. They could also include cloud servers or cloud hardware, some storage devices there. Now, this IoT environment is giving us a scope of, let's say, we are now living in Industry 4.0, right? Which will give us, you can see now the last one is all about cognitive IoT. Now, in cognitive IoT, you can see data and ambient context, right? Meaning of that data. For example, the Lambda, Google's Lambda or ChatGPT, right? They are able to correlate, let's say, few sentences that you are talking to them, and they are able to understand the meaning of that, give you another set of sentences or text by using the pre-trained model that they have, or by using the database that they have, so that you are feeling happy, right? You are able to make out that yes, this chat GPT or Lambda is really intelligent, okay? Or to that effect, deepfake, right? Deepfake is also helping you to generate new videos, but of course people are using it for wrong reasons. That's a different story, but yes, it is again using ambient context. Now let us look into the architecture. How should we develop these IoT platforms, right? So at the bottom layer, the lowest layer, you have sensing devices, sensors, RFIDs, those tags, right? Which you can see in a lot of our cities when these animals, right? Those cows, buffaloes, right? They all roam around the roads, busy roads. The government people, police department, or maybe the veterinary department, they come and put those RFID tags on those animals, right? And they are identified through those. Even RFID tags you will find in your library books, through which those books are all, you scan it immediately, it will be sensed or known, right? You can also have a sensor network for sensing those physical parameters. Even you can use these global positioning systems, GPS systems, to track the positions or the locations of different people. So once you do this sensing layer using these technologies, you need to have a networking layer through which you can pass this information to either a cloud computing platform or to a fog node, right? I'll talk that fog node shortly in the next image. And in the back end, you can develop a lot of interesting or intelligent applications. For example, it could be merchandise tracking, it could be environment protection, intelligent search, telemedicine, intelligent traffic, smart home, etc. So some of the applications that we talked can be built by using this IoT architecture. Now see here, so as your FDP is all about cloud, fog, and IoT, you can see this diagram where, so fog nodes are nothing but another intermediary hardware or nodes which are there between cloud and the IoT devices or IoT nodes, right? Of course, IoT node also you can call as a fog node, but this fog node is not too far from the cloud. So it is possibly nearby or sitting on the edge of your IoT network, and whatever pre-processing or intelligence that you want to develop in these fog nodes, you can do all that. And even two fog nodes can communicate amongst themselves. And finally, some of these processing you can offload to cloud, where you can go and develop the next level of abstraction for your application. Okay. So if you are using, for example, a gateway, which we have used in our IoT prototype development, we can call that one as also a fog node. Now let me go over and say something about how do we do this development, right? So we have several objects, as I said. Now we need to do a sensing. So this is all about observing the environment and then learning from this observation that you have done. It could be context-aware knowledge discovery. You can do a bit of analytics. You can also get some learning from the social world, and then you take a decision and carry out an action. And this process you go on doing continuously. This is basically the cognition cycle that you can see in the left. But now, using this cognition cycle where sensing is involved, then you have learning is involved from the data, and of course then there's a decision making and finally carrying out an action. You can develop now a human-centric intelligent society. So let me give you play a video for you, which will give you an understanding of what is human-centric intelligent society. If you are developing as an application, it should be usable for human. Humans should like it. It should be good for the society, right? Otherwise, it will be of no use. Hence, you will not be able to generate money or wealth from the technique that you are developing. So let me just play the video for you.
Internet of Things promises huge new opportunities.
So is the audio reaching to all of you?
Wearables, smartphones, cloud software, and physical sensors using predictive runway process can have a huge impact on the quality of care received by a critically injured cyclist. The cyclist has had an accident and sustained a serious head injury. Treatment is required as quickly as possible. Let's see what might happen today. It is several minutes until the car passes and the driver calls for an ambulance. The ambulance is dispatched. Due to unclear location information, the ambulance cannot find the location of the incident, wasting precious minutes. Paramedics stabilize the patient and the ambulance starts the journey back to the hospital. Paramedics do as much work on the patient as possible, without access to medical records. With time of the essence, the ambulance gets caught up in the traffic jam, forcing delays and losing valuable time. After finally arriving at the hospital, paramedics discover no staff available. The patient needs to remain on a trolley until doctors become free to keep more time. In this scenario, with all of the delays and lack of information, the outlook of the patient is not good. At Fujitsu, our vision is for a human-centric intelligent society. What does this mean, and how can it help us cyclists? By combining the connectivity of the web with the power of cloud computing, we can integrate infrastructure, information, and people to deliver human-centric systems. In this scenario, Fujitsu Runway process is used to integrate sensors, information systems, and people in order to transform the end-to-end emergency response. Hop Ubiquitous provides Bluetooth smart sensors with IP version 6, CoAP, and RNA capabilities. These sensors collect a combination of acceleration, cycle cables, and heart rate data from both the cyclist and the bicycle. The cyclist's smartwatch correlates its data and detects that a serious accident has taken place. In a split second, it uploads it along with GPS location and the cyclist's key medical information to the Fujitsu Runway process cloud platform. The platform first raises an alert to the 112 service using the recent EENA standard for emergency services. The control center recognizes the severity of the incident and dispatches the closest ambulance. Next, the platform verifies live traffic status using sensor data from the Smart City Operations Center and calculates the quickest route to the accident. The cyclist's location and the optimum route calculated using traffic data are pushed to the ambulance. The estimated time of arrival of the ambulance is sent back to the smartwatch. Immediate notification of the accident coupled with a precise location and optimum routing means that the ambulance reaches the cyclist several minutes earlier. The ambulance heads towards the hospital. Using the recent AMSOS standard, the platform requests the cyclist's medical records from the hospital and pushes them, along with the accident information from the sensors, to the paramedic and the ambulance. Through connectivity, the paramedic is able to optimize treatment en route, while also keeping the hospital updated in preparation for arrival. With every second counting, traffic congestion suddenly breaks down ahead of them. But before they hit it, the Smart City Operations Center notifies the Fujitsu Runway process platform. The platform in turn contacts the 112 service and finds the best alternative hospital with available staff. This hospital is further away, but it is now the quickest route to treatment. When the team arrives, the staff know the full extent of the cyclist's injuries and his medical history, and they spring into action. These technologies are not futuristic, they exist today, but it is through connecting them together that vital minutes can be saved, and the life of the cyclist. Human-centric innovation connects people, information, and infrastructure. With this approach, we can build a better place to live, a better place to conduct our business, a human-centric, intelligent society.
Fine. So hope the audio was heard by everybody, right? Audio was clear.
Yes, sir. Okay, a little bit low here, but it was audible.
Okay, so let me just summarize what this video was telling, and then I'll go to the next slide. So basically, it is an application from Fujitsu, run my process, right? That is the name they have given. And there was a cyclist who was driving on the road. Now, if he is meeting with an accident, right, without this intelligent application, if it is the normal or the standard way, somebody is seeing the accident and then calling a ambulance service, like we have 108 here, right? So ambulance is again taking its own time, right? If your ambulance is farther from you, it will take time. If it is nearby you, it will take less time. Ambulance is coming, then taking the patient on the ambulance and going to the medical. So on the way, let's say there is minimum help the ambulance is able to provide to the patient. If the accident is severe, possibly the other aspects of treatment that he needs, right? Immediately, so over phone only the communications, etc., will happen. But there is no information which is integrated into this, right? For example, who is this patient? What is his history, right? Or what are the other complications this patient have suffered over last few years? Who were the doctors who were treating him? Which were the medicals to where he was going, etc. All those things were not available, right? And then possibly he's getting into a traffic jam, going to a medical where doctors are not there, taking his route again, diverting to another medical, getting treated there, right? So a lot of issues have come up in the middle. Now, if you want to do this activity through intelligent means, right? So here, your sensors are nothing but those sensors which are fitted on probably the heart, right? The pulse rate or heart rate, they can tell whether the cycle has stopped or not. There is a sensor, it can tell. And the Fitbit watch or the smart watch that the cyclist was wearing is, you can call it as a fog node, where that watch was detecting, yes, there is an accident. Why? Because the speed of the rim or the cycle tire is 0, and also the pulse rate or the heart rate of the human being is not stable because he has met with an accident. So there is a program which is running on that fog node, which is the smart watch, and it detected that there is an accident. So you don't need any third party to detect that there is an accident here. And the smartphone has also communication capability. So it actually alerted your ambulance service, right? And then possibly automatically an ambulance comes to this place. And now once the patient gets into the ambulance, there is a this to run my process. So it's basically that program is running on a cloud, on a probably a city center or some centralized location within that city. Now that cloud application knows a lot of details possibly about this patient, and what should be a good treatment plan for this also is coming automatically from that cloud service or from that run my process application. And when the vehicle is moving towards the medical, possibly this run my process also tracks the vehicle movement through a GPS or through some sensors, right? And figures out or finds out that there is a traffic jam. It diverts the van or the ambulance to another route, and finally it takes him into a right medical where he gets treated. So this is all about IoT, fog computing, and cloud computing, and hence a nice or a smart healthcare application you could see here through this. And hence for whom it is designed. It is designed for human being only. So hence it is called a human-centric intelligence society. So I think our objective is for this type of thing. Anyway, so we will see what I will also explain what things we have done here on this platform, right? Now probably Fujitsu is a Japanese company where that application is running maybe on some cities in Japan, or maybe also you will find this in a lot of developed countries, the smart health. So we in India, we have Indian government have come up with smart city mission, right? Maybe the BJP government, right? Over last 7-8 years, this mission started. So you can see when 100 smart cities are planned. For example, cities like Bhopal, cities like Surat, Ahmedabad, Bhubaneswar, right? So these are all a set of cities. I think I'm naming 5 to 6. There are actually 100 cities which will be converted to smart cities, right? And if you say it's a smart city, this is what all things it should have? It should have smart water, right? Smart transportation. One example you saw for smart transportation, right? Or smart healthcare. You can put into anything there. Smart building, smart energy, smart education, smart waste management, smart safety, etc. All these, right? So basically, the word smart means intelligent, and all these things are actually essential for a good living of developed society. Now, in my maybe recent trip to my hometown, Bhubaneswar, I saw amazing applications which were being developed by the state government on that capital city of Odisha. You can see there are two images which I have taken from this government website. The down one is all about the water conservation, right? Rainwater harvesting. So the government has a scheme where there are a lot of pipes which have to be used and channels which have to be made built for taking out the water that gets accumulated in the rooftop during rainy season, and then it stores that one. If you have a well on your house, it will go there to the well, or it can go to a tank as well, and then of course with a little bit of filtering, etc., it also does to that water. And maybe the scheme is nice, where somebody, a household, has to apply for that particular service, and maybe you have to deposit some minimal around 20-25,000 rupees for a total cost of 1.2 to 1.5 lakhs for making this happen. And I think people are coming spontaneously or by their own to get this rainwater harvesting system installed on their homes. You can see the down one as an image. One more application also I saw, like solar energy, right? Solar panels were fitted on the rooftop, through which you can generate your electricity and other power or energy for your house. And you can see world's largest rooftop solar initiative unveiled. Free power to millions. How will free power transform the lives of 10 million households? Right? This is again coming from my Bhubaneswar. It was a message on the Twitter. Right? You can of course go to the smart city offices or websites of all these 100 smart cities of Indian planned by Indian government, and see how much they have progressed. And I think if we are positive, we should not take more than another 5 to 7 years or maybe 10 years to make 80 to 90% progress on this aspect. Fine. With that, I'll now get into another complex issue, that is, what are the top IoT concerns? So to make these applications realizable, right? All the smart health, smart water and all, we need to use IoTs, right? Maybe those fog nodes, cloud services, those sensors, and of course, a bunch of AI ML programs. Otherwise, it cannot be smart or intelligent. Right? So there are multiple issues when one thinks of. You can see right hand side, there is a smart car hack. So the car which is fitted with a lot of sensors, right? Maybe it is whether it is a driver less or with a driver the car is going. If there is a hack that has happened, possibly car has turned into the left. But of course, more use of driverless cars, because we talked about smart IoT, right? When there is no driver and car is going, somebody has hacked it and car has gone into some out of the road. There is a smart door lock hack which somebody can do. Why he is doing this smart door lock hack is to find out what is the entry and exit pattern when people are going into the home and when people are coming out from the home. Possibly, if this information is basically private information, right? Somebody wants to figure it out, then he can do this type of threat to the IoT or the smart door lock. The left-hand side image, if you see, the iScoop is an website which has given these top two concerns of these IoT implementations. One is the implementation, the way you are building or making your IoT hardware as well as software available to your organization, right? Should we use LoRa? Should we use Arduino? Should we use Raspberry Pi? Should we use sensors coming from company 1 or company 2 or company 3, right? For example, Huawei was the company which was selling us routers, switches, and all those networking equipments, right? After operating over, let's say, 4 to 5 years in India, people discovered that they have a back door where they can hack or they can get a lot of private information of an organization, and hence Huawei was banned from a lot of 5G and other tenders which Indian government was floating over last few years. So that was, of course, on a networking equipment, but who knows, unless we have our own capabilities on developing these sensors and IoT platforms, if we rely on the hardware manufacturers or software manufacturers, we might end up in getting into some of these troubles. So security is the second challenge here. 34% is implementation problem, and 25% is security, and the rest all you can see: initial purchase, scalability, etc. Now let me give you one example of a buffer overflow which is possible on these IoT devices. Now in this function you can see there is a string copy, strcpy, where whatever you have given from command line, right, arg1, you are copying into buffer, and buffer is nothing but a 4-character array. So if you give auth me exclamatory sign, auth me exclamatory sign, auth is going to buffer, and the remaining part of the string, that is m, e, exclamatory sign, and the null character, these 4 characters are going to the non-auth area, right? And if you see now the code part where the programmer does not want to get into non-auth by using this logic, but because of buffer overflow, the non-auth part, the if condition will be activated or we will be running, because it is not null. It is having me as a two character string. So you will basically get into the code part and it will be executed, right? So this is how the attacks are possible, because you created a buffer. So it is all because of your string copy, right? That is the culprit. All these are possible. There are multiple such attacks which are possible on IoT systems. Fine. Now let me go to what we have done on these IoT, cognitive IoT build-up, and the security aspect of in our lab or in our department here. You can see here there are different type of IoT hardware that we have used. They are all embedded boards, IoT nodes, as well as they can act as gateways. For example, Intel Galileo can act as a gateway, whereas Intel Atom, the lower end version of this Galileo, can act as a simple IoT node. So when I say gateway, it has the power to receive data from several IoT nodes and then process it, do a little bit of pre-processing, and then send it to a backend server or to a cloud service. So you can see in this slide, we have used Raspberry Pi, we have used Intel Galileo, we have used Arduino, and the fourth image, the leftmost top, right, is basically connecting several sensors to Raspberry Pi, right? We used group interface to this Raspberry Pi to connect those sensors. So sensors, yeah, you can see here in this, the test bed, possibly that was my chamber B220, where over a printer, we kept one Intel Galileo board with a lot of sensors connected to it. So sensors like humidity sensor, luminosity sensor, which can sense humidity in the room, temperature in the room, light in the room, right? Even motion sensors, people coming into my room, right? These were some 4 to 5 sensors which are connected to that board. You can see another lab, Intel IoT lab. As I said, Intel has also funded us on some executing some part of this work. So we used a lot of Intel boards there in the Intel lab. You can see on the door there is a sensor which will basically give us how whether the door is open or not, whether people are coming inside the room or not. There is a sensor which is for energy meter, which was fitted on the for AC, right? That was on the wall, and there are a few sensors which are fitted on the computing devices which are there running on that lab. Now downside you have 3 images where we have a server room which is a mini data center, right? So there you can see over a table we kept one IoT node with sensors like, again, humidity, light, right, temperature, because we wanted to know whether the temperature in the mini data center is around 16, 17 degrees or not, right? So we collected those physical parameters, and then of course we had similar type of devices in this intelligent systems and networks lab, the lab from which my group works. So we connected all these. Then what we, of course, some of these IoT nodes we used as gateways. Possibly, for example, there was a laptop which was there in the Intel IoT lab where we used it as a gateway. And of course, one of these IoT boards also we used as a gateway, maybe a Raspberry Pi as well as Intel Galileo. You can see here some of the code that we wrote. We used socket programming, we used Python scripts, right? We used C programming. All those we used and wrote our developed our application. For example, in the top part you can see read light in lux from light sensor, right? So the Intel's MRAA library is used here, right? Where we are initializing a particular pin of the sensor from where we will read the light. And there is a for loop, which is an infinite loop, and the raw ADC value, right? We are reading data of light. It's a raw value, and then we are converting that one into a volt. You can see the formula which is used. These all things come from the manufacturer. How do you convert that raw value to a volt? Then we convert it into resistance by using another formula, then into lux, and then that lux we are sending it. So there is a structure. We are sending it through that data, writing it into socket. And of course, it was again a client-server based programming where the data collected by this IoT board or IoT node was sent to the server. Similarly, we have temperature in Celsius. From a temperature sensor, you can see the down one, where again Intel's MRAA library we used. See MRAA underscore AIO underscore read. So this is basically an API or a function that you are using, and then you are passing the argument as ADC underscore A0. This will help you in reading data from that particular port, and we get a raw value, convert it to volts and then to Celsius, and then we display certain thing on the screen, and then we write it to the socket so that it can go to the server. So it's, as I said, we are collecting all these at a gateway. Now, so this is basically visualization how our prototype was looking like. You can see users connected to this site. So these are all the IP addresses which you could see here. Then the power energy chart, you can see that was also coming, right? The IoT lab, what is the temperature, what is the light, right? B224 office room, what is the temperature and what is the light, right? That was all coming here, there. Maybe when so the values are all differing in these. And then there was also a visualization which was also coming here. From the server room, mini data center, what are all those temperature values, light values, all those we got. Right. Now we also use this R Studio for developing, for building these association rule mining, right? To intelligently discover those patterns where we could carry out certain ML work. Just given, so we need to basically find out the correlations. If AC is this much, right? Temperature is that much, then what should we do next? So this is how we built a CEP, complex event processing engine. Right? Now let me explain what is the meaning of a complex event. Now, one event could be of this room is, let's say, for example, what is the temperature of this room that you are measuring? This is one event. How much light is there in this room? You are measuring that. That is another event, right? How many people are there in this room? You are measuring that. That is also another event. Now, using these events, you are now understanding some intelligent actions, right? You are deriving a rule. Maybe you are building a decision tree, or you are using a regression model, or you are using a neural network to that effect to uh, understand the pattern so that you can decide on the actions, the intelligent outputs that you can figure out, right? So, for example, if these many people are there and these are the values of those physical sensors or those physical parameters, what should be done next, right? Or what could be the possible actions that you could come up, right? So alerts or actions you can generate there. For example, if you are doing energy conservation, depending on the number of people who are using those computing devices in those labs and the power that is remaining on those computing devices and the applications that are running on those computing devices, you can decide to power off or shut down few machines or few applications from those computing devices. So this type of output or alerts you can generate. Now the architecture that you can see here in the, so we used, let's say, telegraph to read data from those sensors, right? We used a influx DB, which is a real-time database, right? Where this telegraph was writing that into this, where we used Kafka, which was a distributed broker model, where to communicate with the CEP and other entities, where simple event streams were recognized there, and then complex event streams were produced by CEP. Now, maybe one or two publications I have given in this slide where you can get more details about these things. You can see one visualization of our where we can see whether the door is open or closed, right? How much is the luminosity? What is the temperature, right? The Fibaro is the company. Wall plug energy consumption, how much is it? So this is some sort of visualization that we did on this. Now then, what did we do is, I'll show you now a demo of how did we implement this, right? And then maybe I'll summarize at the end of that. So there is no audio to this. It has a simple run of those applications. So as we run, I'll go on telling. So maybe we are running the CEP Rust engine, right? So basically, this is our CEP engine. The server is running this. We are compiling the CEP server, and then it is running here. We will define now rules, right? So these are all in the JSON format. You can see added new rule. So this is rule 1. Like this, we will have 5 to 6 rules. So these rules will help the CEP server in understanding how to mix up those simple events to generate those complex events. As I said, these rules could come from association rule mining algorithm, or it could even come from a decision tree based learning algorithm. If you have those labeled data set. So we are starting the server now at port number 8000. And here you can see in the next one, this is the gateway node. All the running Linux OS. Maybe again a Intel Galileo board. And we are running a Python script there for this gateway. So CEP server we started first. And then we are starting the gateway, which is actually controlling those IoT nodes. So gateway also started. Now this is nodes, IoT nodes. See, the IoT lab's temperature is now coming here. 29 degrees Celsius, 25. So these values are also going to, you can see the rules are written, right? As the temperature is changing, the actions are being taken as open the door. Action is open door. IoT lab. Then we started the two more nodes, node 2 and node 3, where in node 2, we are getting the CO. And CO sensor value. Here we are getting humidity value. One more just now we are starting. This is also humidity, but this is location is outside. Previous one is location is inside. That is the IoT lab. You can see there the. So it is all this data is going through gateway to the server, and at server CEP engine is running, and the actions are being. So the actions could be open the door, open the windows, right? Switch on the AC, switch off the AC. These are all the actions that we have defined on those 5 to 6 rules that we initially created. You can see it is continuously going on, applying those rules based on what these 4 nodes are sending. And of course, in this architecture, this is basically a cognitive IoT setup that we did. We used RStudio, we used those Python and C codes to develop this. The gateway that we designed, which you can of course call it as a POP node, was also smartly deciding the IoT node from whom it should receive the sensor data. Suppose one IoT node is down, it can start another IoT node, and maybe also it can also understand the power availability of those IoT nodes, and then it can also switch off one of those end device, use another device. So there was a script doing this also at the gateway node. Fine, with this, I will now get into the security aspect. Let me just pause for a while and ask if there are any questions from any of you. All right, let me go to the last part of my presentation where I'll talk about what security thing that we did in this project. And you can see this is ROP, right? The short name is ROP, Return Oriented Programming. This is a technique, or you have a ROP compiler. This was one of the tool that my collaborator from VU, Virgin University Amsterdam, Dutch professors, right? His name was Herbert Boss, right? The Tannenbaum's group in VU. So they were very strong in system security side. So when we proposed this project maybe 8-9 years ago, nobody had used ROP to defend the code, defend the programs, right? Which were running on, let's say, computing devices, including IoT devices. People were using this ROP to attack or to hack another computing device. And this was actually a tool which was developed by European University, and finally it is now available in US universities as well. Researchers have developed much more capabilities to these ROP compilers. So you can see here, so I'm explaining here what is the meaning of ROP. If you have a assembly code like right hand side, test 0007 EDI register, and then set NZB some EBP, right, register. This is assembly code, let us say 86 assembly. Now its machine code is there in the left hand side, right? That is written in hex F7, C7, 07, then 000000, then 0F and all this. So what you do now is pick out only this part of this machine code. Start from C0 and go up to C3. C3 is basically a return statement. Now if you can use this and manipulate your call stack using these, right? This is basically called as a ROP gadget. So what it will give, you are basically rearranging this by leaving that F7, the machine code for test. C700, then 3 pairs of zeros, then 0F. You take this as, so now that first line becomes move well EDI to some address. 95 is for exchange, EBP and EX, they are the registers. Then 45 is for increment EBP, and C3 is for return. So by simply choosing that part of the code, you are doing this much. But now when you do this, your meaning of the original code does not change, right? Because the same set of instructions are there. But only thing is, what have you done? You have manipulated the call stack by finding out a gadget like this, where of course each of these ROP object or gadget should have a C3 or a return at the end, so that you can go back to the caller's address. So now let us see how it is used. Building the ROP tool. Maybe there is a function which is F1, and now I have on the same program I have other parts of my code. So what will I do? I am now trying to augment this function with ROP chain. Basically, I am creating another set of gadgets and chaining them together without changing the meaning of the original code. So if you run the ROP augmented code, it should give you the same output. But the hacker or the bad guy who wants to tamper your code does not know this ROP chain. Hence, when he injects some code into your ROP augmented code, it will stop, or it will give you an alert, because your ROP chain will flutter or will stop or will get disturbed in the middle, right? This is basically the trick. So we used a ROP tool or ROP chain for defending the code. So what is the meaning of defending the code? It means if there is a code which is running on the IoT device, let's say I am wearing a SpO2 sensor on my body, but actually the oxygen content or SpO2 content it should give is this much. But now the hack has happened to that device and it is giving some different value, or somebody is using a pacemaker which is electronically controllable. and if it is hacked, right, and some bad program runs on that pacemaker, possibly your heart will stop, so the patient will die. Now what you can now do is on all these IoT devices, maybe as I said, a door lock hack, electric bulb hack, right? If somebody hacks the electric bulb, which is IoT bulb, right, he can find out what is your Wi-Fi login and password, and it is dangerous, right, if your credentials are leaked. So these are all the issues which could come up. So what you do now is the function of the program which is running. Yes, ROP you can add or inject into either the source code or into the assembly code or into the machine code which is running on the device, depending on your need. So we tried with both assembly code, as I showed in the previous slide, and we also did with the source code. Let's say C program, we augmented it with ROP, and then we compiled and ran that code. So my objective is to make this ROP augmented function. So I just wrote ROP of F1. Then I need to now add these two instructions: move ROP of F1 to ESP and then return. Right? Otherwise, you are starting from ROP and then coming back to the place from where you started. So these were all again my gadgets. Then what will I do? I will now choose gadgets from these regions. So these are all the one that I showed in the previous slide, where it was starting with move and ending with return. So G1, G2, G3, G4, G5, 5 different gadgets. So gadget is nothing but a small piece of code from your original code that you have carved out, you have found out. For example, adding 2 registers, or adding 1 to the content of a register, comparing 2 registers, right? Moving data from a memory location to another memory location, moving data from register to memory location, right? So where all these should have a return instruction at the end, so that you can manipulate the call stack. Now what will I do? I will chain these now. So you can see the linking. So this function is calling G3. G3 will call G1, G1 to G2, right? So now by making this chain, whereas G4, G5 I have not used. Now these are all called as overlapping gadgets. They are basically overlapping with some part of the other code which I have not included in the ROP chain. Now if there is any hack that has happened to this or any, so it is basically code tampering, right? Somebody changing our code, like a buffer overflow or a code injection attack. If there is a tampering or modification that has happened to this code, then this ROP chain will disturb. Now as ROP chain will disturb, you will get an alert. So we built a tool. You can see the run of that tool. Maybe one image I have taken, the demo, where we are making available all those ROP gadgets and then making a ROP chain out of that. So unfortunately, I don't have a demo for this. I was having, but then because of paucity of time, I will not be able to show that demo here, the ROP demo. Now what we did next, using ROP, we defended our code from getting tampered by a bad person or bad guy, right? Now these ROP gadgets that we are choosing, how should we make sure that these ROP gadgets that we have identified from our original program are the good ones or are the critical ones, important ones? If I have created a ROP chain by using gadgets from some part of the code, but the hacker is targeting some other part of the code, then I'll be in problem, right? Still my code is vulnerable, or it is not tamper proof. Somebody can tamper it. Hence, we went by carrying out a lot of code profiling activity. We used Intel's PIN tool. We used a lot of debuggers, open source debuggers for doing this code profiling. So what are we doing through this is, we are trying to find out the hot code and cold code. So what is the meaning of a hot code inside a code? Maybe a code which is run more frequently, a cold code which is run less frequently. So sometimes the attackers target also that both the codes, hot code as well as the cold code, because out of 1 hour of your program run, 80% is a hard code portion is being run. Let's say there is a for loop, infinite loop, and it is running continuously, whereas other part of your code are not running. Hence, people may target that loop part. So identify these different portions, and then we used also other stuff like we used a bit of heuristics, state analysis, control flow graphs also we used to figure out which are those functions in my code which are important for us, so that we can take out the overlapping regions of that function as our ROP gadgets. We also used, let's say, check summing approach, another technique. We also used canaries to, maybe the canaries are like the signatures which you will find in the functions. We used again some of these techniques. I think on my own homepage, the publications list, some of these publications are available, where you can see those techniques for improving on this ROP chain augmentation. So this was one of the projects that we completed, which was a collaborative project with the Dutch guys, where these METI and NW supported with Cisco and Progress funded us for this work. Okay, I'll go to the next project that we did or I'm doing currently, which is about W bands, wireless body area networks. Maybe this is a 1 year or 1.5 year old project. Another 1 or 2 years are there on this. As I said, this was from DST's National Mission for Cyber Physical Systems scheme. And you can see an image here. There are a lot of sensors. So wireless body area network. You have fitted a lot of sensors on the body, which are all sensing the biological markers, right? The health parameters from the body. Something is in the chest, something is in the leg, right? Just like our Fitbit watches and all they do. So now you take all those. Okay, so what we are doing here is, in a W band, these devices or sensors that you are putting fitting onto your body, they are basically sensing certain physical parameters or health markers from your body. But these values, they have to send to somebody, right? So one of these nodes have to act as a sync node or act as a fog node. You can also call that node as. So for example, my mobile device, which I have kept on my table here, which is very nearby, the body sensors can send it to my mobile device. So one part of the work that we are doing here is, how does these sensing devices which are fitted on the body get authenticated by my mobile device? So why should my mobile device rely on a value that is coming from my Fitbit watch, let us say, or from some sensor which is fitted in my body? How does it make sure that it is coming from the right source? So this is basically an authentication part. So that part I have not brought into this presentation. So you can, of course, develop lightweight protocols for authenticating these devices to the sync node or to the fog node. Now, of course, as it is a W band, as I walk out of my room with all those sensor devices fitted into my body and my mobile on my pocket, right, pant or shirt pocket, and then I'm going out, still all those physical parameters are collected on my sync node. So authentication is one part. The second part that we are addressing is these anomalies, right? Anomalies are nothing but the abnormalities or the wrong values that could come up from these devices. So let's say my Fitbit watch or the sensor that I have fitted here for giving my pulse rate should give me X value, because that is my correct value. But that X is modified to X plus 100 or X plus 50 or 2x or 3x. So those I'll call as anomalies, right? Which are not actually true. Now, what are the different causes for those anomalies? Anomalies could come because of the sensor faults, right? Because of damages to the sync nodes communication link with the sensor that you have fitted, right? But these anomalies are unavoidable. You can't help. They're all the real anomalies. But the anomalies could come also by a bad guy or a hacker or a person who wants to create trouble for you. So he will change your value from, let's say, 30 to 330 or 20 to 120 or 85, something, right? So if he is changing these values of one sensor value, first question is, how do you detect it? Next is, by changing the value of this sensor, does it also create some problem with some other sensors values, contextual anomalies, right? For example, the pulse rate and heart rate, if one is changed to some other value and other is not changed, it is remaining in the original state, you can easily catch it, right? So our purpose is to identify these anomalies or outliers in the data that is collected from a W band. So you can see there is a, okay, all these are of course going to a cloud or to a server through or to a remote data center over internet from this fog node or from this central unit, which is maybe I said my mobile device. So how do we do this? Maybe in one we have used here is you can see we have used this is basically a work which got accepted and we have registered also. And my student, who is the first author, is a undergrad student. Karthikeya will go and maybe make the presentation in April in Kitakasu, Japan, right? Which is again a Tier B conference, right? 38th International Conference on Advanced Internet Applications. So anomaly detection in double bands using CNN autoencoders and LSTMs. These long short-term memories, and we have used CNN autoencoders to do this. You can see here CNN. Now through this CNN, what we are doing first is given a bunch of data items, right? These having anomalies and not having anomalies. It is basically finding out what are those features that it should use to identify those anomalies or outliers. And then we are using LSTM model, right? I will not get into the details of these algorithms or these models. You can see there are different layers, right? Let's say max pooling layer, convolutional 2D layer, right? Then ultimately we get this encoder output as a latent space. That is nothing but our features, reduced features or important features that are required to identify this anomaly. Finally, you have a decoder also for this CNN, which will also regenerate the input that you have given there. So through this, what is happening? The weights that are there in this network, ANN or neural network, are now getting stabilized so that they are identifying the important features that are required. And then LSTM we have used for identifying the contextual anomalies or the correlations between one sensor value and another sensor value. You can see here, this is how the you can see contextual anomalies, right? They are predicted through here. The magenta color in the diagram. And then we also have used developed another work. Again, this is with help of my undergrad and master students. We are using generative AI, that is GANs, which are having two different components, generator and discriminator. So fake samples are generated by one, and they are compared with the original samples, and then how great these fake samples are identified by discriminator. And if the generator can fool this discriminator, then the purpose of generator is solved, right? It is able to generate those fake samples. But if it is not, then in that process, the anomalies will be detected, right, by the discriminator. So we have used, you can see in the downside, there are a few graphs which are all telling anomalies on different, let's say, for example, heart rate reading, SpO2 reading, and the first one is in blood pressure. So we used actually an open data set which is available on Kaggle, Mimic 2, as well as Mimic 1, where we had all these labeled data of different patients on healthcare data. And then we built these models to detect those anomalies. And with these, I think I have also recently finished or guiding one PhD on doing this distributed machine learning. Maybe the next 5 minutes or so, I'll talk on this distributed machine learning, what data, what we have done, and of course the algorithms that we have developed for be it anomaly detection on double bands or the cognitive IoT part or the rock chain part. We can develop or build all those algorithms using distributed machine learning as well, right? So let me give a typical example of, or distinguishing here what is centralized learning, what is distributed learning, and what is federated learning, which is a type of distributed learning. Imagine we have different medicals here in Hyderabad, right? One is, let's say, for example, Apollo Medicals. Other one is, let's say, Yashoda Medicals. Third one is Medicity, right? There are multiple such different medical chains which are there in Hyderabad. Now, each of these medical organization, right? They have their own set of patients, they have their own set of processes, they have their own set of doctors, and they have their own set of recommendations or treatment plans for different patients. Now, if you can integrate or if you can mix up, right, the learning of all three different medicals, be it Medicity, Yashoda, and Apollo, possibly each one can learn from others' functions or others' experiences. Hence, the overall treatment by all these medicals will be good. So this is a sort of, so when I explain the second part, that is nothing but distributed learning. So let us take this to our machine learning here. The first diagram that you see is there are different clients which are all, for example, I have now IoT nodes, only small sensors only, right? Fitted into those Intel Atom boards, which do not have much capabilities. They can simply sense and send it, communicate it to another central server. Maybe it could be a fog node or a server which I have put inside our premises, right, in our departmental server room. Then I am building my machine learning model there. So data is getting uploaded from all these clients. I am building there, and then finally, the actions that are to be taken by these clients, I am informing them, or whatever output I need, I am getting it from my server. So this is all central learning, right? Whereas now, if you do a distributed learning, let all these clients not only send data to the central server, they do learning by themselves, right? So client was using, let's say, so these are all neural networks that I have given the images. Client 1 is making its own model, client 2 is making its own model, client 3 is also making its own model. Maybe decision tree, all of them are running, right? So, or different type of algorithms also they are running. Then they are uploading this model to the central server, and central server is communicating those parameters to back to all these clients, and all these clients are using those. So this is basically called as a distributed machine learning. Whereas now, if I extend it to the next model, which I'm talking as federated learning, here you can see the central server not only sends the parameters or informs everyone's output to other one, it actually builds a model, or it generates or creates a model. Maybe it averages out, builds a global model by doing an aggregation. Maybe again it has a neural network there at its end, and that information is sending back to all these three clients. So this is basically much more powerful than the central learning approach. You can see two of our publications on this space. So maybe I have 2 more slides. I'll finish it and then I'll stop. So if you see an application of this federated learning, what I explained in the previous slide, the first client is now learning by using only 2 rows of my data set. The next node is learning by using the third. So if I have 10 records, I'll put 6 records into one IoT node, 4 records into another IoT node, right? Of course, if I have different type of records, that also I can do. That is what you can see in the second image. And each of these client is now sending a shared model state in the predicted learning. So the second diagram is saying now clients are nothing but your workers. Worker 1, worker, so second worker is there. You can see the images are, one has an image of a dog, which is wearing a spectacle, and the second image is a cat, not a dog. Now these two images, right, or these two animals, creatures, their behaviors, the physical appearances are not completely different, right? There is some similarity, there is some dissimilarity. So what this server will do in the predicted learning is, it will, so each of these worker is making its own model, right? They are now sending this to the server, update model with the local data. So how does a dog look like? This information in terms of a neural network learning, right? The weights, the number of layers, the number of nodes, what is the activation function, right? What is the loss function? What is the optimization function for that loss function? All these are passed to what is the learning rate? All these are passed to the server. Then server now got this information from worker 1 as well as worker 2. Here it is, second worker is cat. So then it builds a global model by building another neural network with, and that information it is passing back to both of these. So in this process, what is happening? The worker 1 is learning the features of the second worker. Second worker is learning the features of the first worker. So this is basically about predicted learning, where the models also get built at the server side. This is my last slide, where we can see we have used autoencoders, right, for one-shot predicted learning. When I say one-shot, this is also a jargon or a nomenclature. You do not communicate multiple times with the server. Do it only one time. So in the top diagram, you can see there is an autoencoder which will have both encoder and decoder component. Given an input, this autoencoder will generate the same as the output, right? That is the behavior of autoencoder. Through this process, it will learn all those weights on those layers. Now, once this entire learning is over for the entire data set, we recreate only the encoder output. That is the latent space. Here you can see this is the encoder output, and that each client sends to the server, right? Maybe this is a cloud or a fog, whatever here we have given as a cloud. So there what we do a aggregation of all that and then send back that information back to the clients. So this happens only one time. We don't have multiple times this information is going and coming between clients and servers. Hence, we call it as one-shot FL. You can see the outputs of the MNIST data set with digits as well as the Mona Lisa images or present data set also we have used. So I think with this, I will stop as the time has ended. It is 7:10. Now, for conclusion, what did we do? I explained here is we built a prototype IoT implementation as part of the first project. We also had a complex event processing engine where we used a bit of ML to, and also we had our own architecture, including Kafka and the Telegraph, the InfluxDB, etc., to develop an application for building a smart IoT application. We also had our own technique or algorithm for making a code which is non-tamperable, or somebody cannot tamper that code using raw chains. And we also used profilers to figure out which are those portions of the code which are more important or meaningful to you using profiling. And finally, I talked about the predicted learning using generative AI for reducing the load on all those client nodes and then making it in a distributed fashion. So with this, I'll conclude or I'll stop. If there are any questions, you can ask me now.